Hello, this is Kristina.
This is Jovan.
This is our final project for AI class. We are using a multi-layer obesity classes to explore data sets to predict obesity risk, which is closely tied to cardiovascular disease. By analyzing demographics, lifestyle choices, and healthcare indicators, we aim to build a strong predictive model to identify those at higher risk. The dataset derived from a deep learning model trained on obesity or cardiovascular disease provides numerous features for examination. We use visualizations, clusterings, exploratory data analysis to uncover valuable insights that we can guide to the creation of effective predictive models. We will guide you through some analysis of our dataset with a goal to develop a model capable to identify individuals at higher risk of obesity. The language we have used is Python, and in the first block, we have imported the required libraries that we have used. Panda SPD for data manipulation and analysis, NumPy as NP for numerical operations, from Tubulate import to Tabulate for formatting tabular data, Seaborn as SNS for statistical data visualization, matplotlib.pyplot as PLT for creating plots, matplotlib library inline for displaying plots inline with Jupyter notebooks, and we're also importing warnings of .filter warnings, ignore to suppress any warning messages. We use _CSV method to read the data set. By using the head method, we show top 5 rows of our training data set. We have different categories that the data presents, such as height, weight, family, history, with overweight and other factors which will help us train our model. Some of the factors in the data set were abbreviated so we can expand them into full form for clarity.
Yeah, and some of those categories are FAVC, frequent consumption of high caloric food, true or false, and then FCVC, frequency of consumption of vegetables, NCP, number of main meals, whether it's like they eat 1, 2, 3, 4, 5 main meals a day, CAEC, consumption of food between meals, if they snack or not, CH2O, consumption of water daily, CALC, consumption of alcohol, true or false, SCC, calorie consumption monitoring, do they track their calories, FAF, physical activity frequency, TUE, time using technology devices, MTrans, transportation use, whether they walk, whether they take a bike, whether they take a car to work or wherever they get to for their daily commute. And so we store these headers in abbreviation and full form, and we print out a little table just so it's more easy and more clear for anyone viewing the data set. And then Kristina has a couple of visualizations of the data she's going to go over.
First, to understand the data, we need to understand the difference between the obesity types, normal weights, and overweight. Basically, their ranges are going to be similar to the same. It's going to be the class between 1 and 2. Their difference for BMI of class 1 is going to be 30 to 35, while class 2 or type 2 is going to be 35 to 40. Anything over 40 for each category will be considered as severe obese. As we scroll down, we can see a graph of those trained know by ISDAD visualization. It's going to be based on the number on each category based on that population. When you scroll down, you will see the gender makeup of that population, how many is female and how many there's male. There's going to be a slight over number of the female by 50.2%, while male is at 49.8%. When we scroll down, we see that weight difference and how that range is going to be between the obesity type and 3 and 2, where you can kind of differentiate the differences. 3 and 2 are kind of similar. There's no difference in there, slightly to none, but any other levels you can greatly see the impact and difference. And that range for the weight is going to be 0 to 120. When you scroll down, this graph will show the physical activity and frequency that these individuals are having in a daily activity. That ranges between 0 to 0.8, and the more is going to be insufficient weight, which they're doing the more physical activity, which kind of explains their high percentage because they're little to no risk. When you scroll down, we see the age, and we see it predominantly between 20s to 25s. Normal and insufficient weight people seem to be younger than the rest. As we scroll down, we see that the mean of each category and where they're standing at with their BMI percentage, it's making more sense to differentiate in each category, as you can see that obesity type 3 is a really high risk compared to that of the insufficient weight. As we're going into the training model, I'll pass it on to Jovan to do more the in-depth explaining.
Gotcha. And so in this part of our notebook, we're importing libraries. So from the sklearn, we import different methods and objects such as the training test split, to split into a testing and a validation set for our data, grid search CV, so cross-validating, seeing which parameters are best for training our model, and then the cross-validation score, accuracy score, encoder for encoding those categorical labels, and a standard scaler for scaling all the data for the model, and then the XGBC classifier. And so the first thing we do is, so we imported our training data and our test data, so we're going to actually drop the ID and the no bias data, the classification for whether that's a string classification for whether they're obese 1, obese 2, underweight, or whatever. So we don't want the model seeing that because obviously it's going to make a prediction for what that is. So we're going to drop that, and the ID is not really relevant. So going to change whether someone is classified as obese or not. And we're also going to separate the training data. So the training Y is going to hold that no bias data, the target variable, for when we're comparing what the model predicted and comparing it to what that person actually is, to see on our validation set how accurate our model is. And then so now here we go, we separate the categorical columns first, so that when we're training our model, we can't, these are like more like true false, like family history with overweight, that's like yes or no. So we're gonna be encoding these categorical columns into like binary values like 0, 1. And so that's actually the next thing we do. So we make the training encoded data. So for those categorical columns, we're gonna actually use pandas to hot encode those, like kind of basically how I said, give it like a binary value so the model can have everything in numerical format. So we do that for training data, we do that for the testing data, and then we just quickly make sure that the training and the test data all have the same columns. They should, but this is just a good check to make sure the models are congruent for training and test data. And then the next thing that we do is those classifications for like obese or obese 1, underweight, we're going to actually encode those into a numerical value so that the model can compare it easier. And then next we're going to split the training data into a training and a validation set, because the training data already holds whether a person is their classification. So we're going to train on the training data, and then for the validation set, which is we have it set to 20% of the training data, that's where we're going to have the model make a prediction, and then at the end we're going to test how accurate it actually was. And then the next step is we scale the data. So some variables are a lot larger, like the weight. So this is just taking the mean, getting the mean down to like an average value, and then making sure that no one value kind of skews the training model a little too much, just getting all those values scaled, taking advantage of the scalar object from this library. And then so now we go into actually training the model, and so we feed in different parameters. So the learning rate, like kind of how it steps through the training data and learns how to make classifications. So we pass in different values of 0.01. There it's more like in depth, like it's fine-tuned, it's looking through like all the values. Whereas with 0.1 and 0.2, it's kind of like more of a range. It's like quicker searching through the data, but it may not be as accurate. So, and then depth, like how deep does it go into the training data and the estimators. So we pass in 3 different parameters, and then we actually do a grid search to see, based on this, which parameters give us the highest score. And in this case, score is like accuracy wise, and those are going to be the parameters that we actually want to train the model on. So after doing that grid search, and then after like fitting it based on the data, and then the Y train is what the actual classification is to get the accuracy, we see that the best parameters were actually a learning rate of 0.2, max depth of 3, and estimators of 200. And so now that we have that model with those parameters, we give it the validation set, and we tell it to make predictions based on all those 15 or however columns. And then we test the accuracy based on what the model predicted and what that classification actually was. And in our validation set, we were actually able to see that our model had a 0.91% accuracy rate. And so I'm gonna pass it over to Fiona to make the conclusion.
Go.
Hi, my name is Fiona, and I am concluding this project model with accuracy of 91%. Numerous studies have revealed a strong association between obesity and cardiological disease, emphasizing the critical need for early detection and intervention. Our study focuses on predicting obesity risk using advanced machine learning techniques and exploratory analysis. We have successfully developed a model capable of identifying individuals at heightened risk of obesity-related complications. In healthcare, machine learning and data mining techniques are increasingly adopted for risk prediction and decision support. They're underscore of growing recognition of machine learning's potential in addressing complex health issues like obesity and CVD risk. Our findings highlight the importance of early detection and interventions in mitigating obesity-related health advertises, particularly CVD. Future research could explore integrating additional data sources and refining predictive models to enhance accuracy and generalization.
That concludes our project. If anyone has any questions, please feel free to drop them on the box. Thank you for listening.
Thank you.